Hello everyone, my name is Supriya. I am working as an assistant professor in the Department of PG Studies and Research in Statistics, SDM College Autonomous Ujre. I am going to speak on the topic that is testing the significance of simple linear regression. Let us recall that is simple linear regression model is a model with a single regressor x that is linearly related with a response y, which is given as y is equal to beta naught plus beta 1 x plus epsilon. So here beta naught is the intercept parameter and beta 1 is a slope parameter, which are unknown constants and they are also called as regression coefficients. Y is the response variable, x is the regressor variable and epsilon is a random error component. We have certain assumptions in a linear regression model, that is the errors epsilon i's are assumed to have mean 0 and unknown variance sigma square and are uncorrelated. And in order to carry out the testing of hypothesis, additionally we also assume that the errors are normally distributed. Now let us discuss regarding testing for the significance of regression. So a very important special case of the hypothesis H naught beta 1 equal to beta 1 0. So where we are testing for a specified value of the slope parameter. So a special case of these hypothesis can be H naught beta 1 equal to 0 against H1 beta 1 not equal to 0. So these hypotheses relate to the significance of regression. So here if the null hypothesis is rejected, then this implies that the regressor variable x is of value in explaining the variation in the response y. Suppose the null hypothesis H0 is not rejected, then it implies that there is no linear relationship between x and y. So in order to carry out this testing of hypothesis, we have two approaches. So one is based on t-test and another one is based on f-test. Now let us discuss the first approach, which makes use of t-test statistic. So here for this hypothesis testing, the test statistic is given by t naught, which is equal to beta 1 cap divided by standard error of beta 1 cap, where beta 1 cap is a least square estimator of beta 1 given by the following expression, and standard error of beta 1 cap is square root of residual mean square divided by sxx. So here the decision rule is to reject the null hypothesis H0 when the absolute value of the test statistic T0 is greater than the critical value from T distribution with n-2 degrees of freedom. Now let us discuss the second approach, that is based on f-test. So as we know that in order to construct a f-test statistic, so we need to follow the analysis of variance approach. The analysis of variance is based on partitioning of total variability in the response variable y. So now let us try to obtain this partitioning. So yi minus y bar, to this expression let us subtract and add yi cap. So let us group the terms. So we get yi cap minus y bar plus yi minus yi cap. To this equation, let us square and sum over all the observations on both sides. So thereby we get summation yi minus y bar whole square is equal to summation yi cap minus y bar plus yi minus yi cap whole square. So we can observe that this is in the form a plus b whole square. So we know that a plus b whole square equal to a square plus b square plus 2ab. So let us implement this. Now let us focus on the third term and let us try to simplify this. That is 2 into summation yi cap minus y bar into yi minus yi cap. So let us expand the terms. So thereby we can observe in the first term we have yi minus yi cap. So the difference between the actual value of the response and the predicted value of the response is nothing but the residual ei. So we can see that in the first term we are having 2 into summation yi cap ei. So here summation yi cap ei is 0, that is from the properties of least squares fit, minus 2 into, so here in the second term we can observe that y bar is independent of I, so we can take it outside. So we are getting 2 into y bar into summation ei. So we know that the sum of all the residuals is 0. So thereby we are getting the third term as 0. So therefore summation yi minus y bar whole square is given as summation yi cap minus y bar whole square plus summation yi minus yi cap whole square. So here we can observe that the LHS is the total sum of square, and in the RHS the first term is called as the regression sum of square, and the second term, since yi minus yi cap is called as the ith residual, so the second term is called as residual sum of squares. So here The total sum of squares, we can denote it as SST. So it measures the total variability in the observations yi. And the two components of SST, that is regression sum of square, which we can denote it as SSR. So SSR, and the residual sum of square, which we can denote it as SSRES. So the two components of SST measure the amount of variability in the observations yi accounted for by the regression line. So this is SSR, and the residual variation left unexplained by the regression line. So this is SSRES. Now let us look into the degrees of freedom of the terms of ANOVA, that is the total sum of square has n minus 1 degrees of freedom because 1 degree of freedom is lost as a result of the constraint, that is summation yi minus y bar on the deviations yi minus y bar. The regression sum of square has 1 degree of freedom because SSR is completely determined by one parameter, that is beta 1 cap, and the residual sum of squares has n minus 2 degrees of freedom because two constraints are imposed on the deviations yi minus yi cap as a result of estimating beta naught cap and beta 1 cap. Now, since we have found the different terms required to form the analysis of variance table, so now we can proceed with constructing the test statistic, that is F. So before proceeding, let us note some of the following terms, that is residual sum of square, which is equal to n minus 2 into residual mean square. So n minus 2 into residual mean square divided by sigma square follows chi-square distribution with n minus 2 degrees of freedom. And if the null hypothesis H0 is true, then SSR divided by sigma square also follows chi-square distribution with 1 degrees of freedom. And we need to note that the residual sum of squares and regression sum of squares are independent. Since we know that the ratio of two independent chi-square random variates with its degrees of freedom forms the F random variate, so thereby by using this definition, the test statistic F0 is given as regression sum of square by degrees of freedom 1 whole divided by residual sum of square by degrees of freedom n minus 2, which is equal to regression mean square divided by residual mean square. So here we can observe that the test statistic F0 follows F distribution with degrees of freedom 1 and n minus 2. And the decision rule is to reject the null hypothesis H0 when the test statistic F0 is greater than the critical value from F distribution with 1 and n minus 2 degrees of freedom at alpha level of significance. So thereby this is the analysis of variance table where we have the source of variation as regression, residual and total. So under sum of squares, we are having regression sum of square, residual sum of square and total sum of square. So we have the corresponding degrees of freedom, 1 for regression, n minus 2 for residual and n minus 1 for total, and the corresponding mean squares, that is regression mean square and residual mean square, and the F test statistic. So thereby comparing the F test statistic by the critical value, we can make a decision. Thank you.